Ha! Welcome back to Wondrous Lab, and today, my lab mates, I'm thinking that we're gonna continue on our problem of International Chemistry Olympiad 2019 about silver chloride. So today problem is quite more interesting because we are going to calculate the equilibrium constant of formation of one complex, and we're gonna find how many ligands there are on this complex. So lots of chemistry, lots of fun. Let's get started. So put your gear on because we're gonna do some applied chemistry. So I'm gonna read to you the problem. So it's problem 4. When ammonia, code D, when ammonia is added to silver chloride, a well-defined complex of stoichiometry N is formed. Write the balanced equation corresponding to the synthesis of the complex AgNH3N, because it's a complex of silver with ammonia. We don't know how many ammonias. From silver chloride, and calculate the corresponding equilibrium constant. So if you wish, pause the video, try to write the equation. Okay, did you try it? Did you not try it? There's no problem, we're going to do anyways. So we got silver chloride, AgCl, okay? So we put NH3 and moles of ammonia, forming the complex, which is AgNH3N plus Cl minus. So this is the equation, is already balanced. We have N moles of ammonia and N moles of ammonia coordinating the silver. So let's try to calculate the equilibrium constant this time. Okay, so to calculate the equilibrium constant, we will need information that is in the beginning of the problem, which is beta n. Beta n is equal to 10 to the power of 7.2. This beta n is the constant of formation of this complex. So what it means? It means that if we have silver here, and we put n moles of ammonia forming the complex NH3N plus. So this is the constant for this reaction. So if we want to represent it mathematically, this, so it's gonna be the product, so the concentration of the complex AgNH3N over the reactants, so concentration of silver times concentration, I'm sorry, my dog is barking, concentration of ammonia in the NF power. Okay, so we want the equilibrium constant of this first reaction here. So if we want to represent the constant mathematically, I don't know, so it's gonna be the same thing, the product, the concentration of the product, so our complex times concentration of chloride over the reactants. So ammonia to the power of n. Okay? So this is, we want this value here. We want this value here. So what do we have in common? What do we have odd with this? This equation here, the only difference is that we have this value here, the value of the constant, and here the chloride, it's different from the silver. So what manipulation we can do with these equations to find our answer? So one thing we can do here, if we take this silver concentration and plug it here and have this ratio here between the concentration of the complex over the concentration of ammonia to the nth power, we also have this here. So we can exchange this information here and maybe we can find our equilibrium constant. Okay? We have it here. We have our information here. So let's plug it here. So using this here, so let's plug it here. Okay? So in the end, our constant is gonna be equal to 10 to the power of 7.2 times concentration of silver times the chloride here that it was missing. Chloride. Okay? So that is our equation. So where do we go from here? Okay? So looks like we do not have a way to go, that there's nothing else we can do. But if you look closely, you can see that concentration of silver times concentration of chloride is the same of the solubility constant that we talked about in the last video. So from here we already have what we need. So because we can exchange this product of concentrations here and plug our 10 to the power of minus 9.7. So in the end, our K is gonna be 10 to the power of 7.2 times 10 to the power of 9.7 minus, which is equal to 10 to 2.5 minus. So we have our equilibrium constant. So it's gonna be K, it's gonna be equal to 10 to the power of minus 2.5. So, okay, we solved the first part of problem. Nice. I'm gonna to clean the board so we can do the next one, because the next one is fairly more interesting in some aspects. So let me clean this. Right, so let me read to you our next problem. Our next problem is ammonia is added to 0.1 mole of silver chloride in 1 liter of water until the last grain of solid disappears. At this moment, concentration of ammonia is equal to 1.78 mole liter. Determine, I guess, the stoichiometry of the complex, neglecting dilution effects. So, what we want to find out in this problem? We want N. What is N? Okay. At first sight, it also looks very crazy, something we can do. So, let's work out this equilibrium constant, trying to represent it with math. Okay, is what we have. I did not put the silver chloride because it is solid. If it is solid, the activity, it's 1. And if the activity is 1, we do not need to represent it because it's going to be 1 times this, so it's this basically. Okay, so let's think in the information we've got. We've got the concentration of ammonia, okay? We've got the concentration of ammonia, and we got the value of the constant, and we also, at first sight looks we not have, but we have the concentration of the complex and the concentration of chloride ion. So why we have this is because in the question it says 0.1 mole of silver chloride in 1 liter of water. So, and every single grain of it had disappeared. So if it disappeared, everything here reacts. And if everything reacts, if we had 0.1 mole of this, we have 0.1 mole of this and 0.1 mole of this. Then we have the concentrations of both products. So it's going to be 0.1 mole per liter because it's only 1 liter. So let's plug every value we have and think on the maths we got to do. Okay, so here is the little equation that we need to work out. Okay, so what it can do? Pass this multiplying and this dividing, so it's gonna be, and this multiplying, and it's gonna be 1, 2 point. I'm sorry, it's because I am very, I'm used to use comma in decimal numbers. I'm sorry if you're not familiar with that, but sometimes I'm gonna make this mistake. So it's gonna be 10 to the minus 2 because this 10 to the minus 1 times n to the minus 1, nothing strange, times divided by 10 to the minus 2.5. Okay, nothing really far away from our what we are used to handle on these chemistry things. So in the end it's gonna be 1.78 to the power of n. It's gonna be equal to this. We can solve it by just 10 to the 0.5 because if it's minus, we can put it plus by putting up, if you know what I mean. So now what we can do, we can use log function on both sides. So we can multiply, you pick this power and multiply it. So it's going to be log 1.78 to the power of n is gonna be equal to, my gosh, log of 10 to the power of 0.5. Okay, nice. Now we can solve it quite nicely. So, and we multiply it, and this we can multiply it too, and don't say, but this is log base 10, and if it's log base 10 and we have 10 here, so it's 1. And we pick the n multiplying, it's gonna be n times log 1.78, it's gonna be equal to 0.5. So n it's gonna be equal to 0.5 divided by log 1.78. Okay, and if you have a standard scientific calculator which we need to solve a lot of chemistry problems, you can just answer it quite nicely. That our answer is 1.99, which is approximately 2. So our n is 2, and then the answer that we all wanted. This n here on our equation It's gonna be 2. And here 2. So our complex have 2 ammonias, and then our silver is complexing with 2 ammonias. There's 2 ligands there, and then we solve it. We do what the problem was asking for us. So okay, I think this video was quite long. Thank you for watching until here. If you watched, thanks. I think this problem. There's more questions, but I guess these are more interesting ones. Maybe I do some other question that is further down on this problem. Okay, so thanks for watching. Kisses. See you next time.